Welcome to this webinar dedicated to accordion craft. My name is Florin Andrei and I will be your host today. The webinar is organized by Accordion Artisans, a non-profit community of craftmasters, accordion repairers, and passionate people eager to learn more about free reed instruments. We'll start with a brief presentation. So I'm Florin Andrei, and I'm part of the Accordion Artisan staff. I'm in charge with the communication and social media. We are pleased to announce that a new member joined the adventure. His name is Uriel, and I will let him tell us more about himself.
Okay, so hi everyone, my name is Uriel Kitai. I'm originally from Israel, but I've lived in Argentina for the past 20 years. I own an accordion repair shop here close to Buenos Aires. I'm also the distributor for the reed factory Voci Armoniche from Castelfidardo in Latin America. And and I've been in Accordion Artisans for the past few months. So thank you.
Okay, so let's give it to Viljo to speak about himself, and after that to Karsten.
Yes, hello to everybody. My name is Viljo Mannerjoki and I'm an accordion artisan from Finland. I've been working with full-time with accordions since 2009 and having my own small workshop in southwest Finland. And to Karsten.
Hello, my name is Carsten Dresser. I'm a master of handcraft and accordion shop owner with a repair shop with a retail of accordions, and also you can rent also accordions by me. I live at the moment in Switzerland, and the German one of northeast Switzerland. Originally, I'm from from East Germany. I made my apprentice in Klingenthal, and yeah, that's to me, and back to Florin.
Thank you very much, Karsten. The topic of today will be accordion tuning, and as a reminder, this is a part of the series of an accordion tuning. And here is our agenda. We have the topic, followed by the Q&A and some social references to reach us. Several best practices we'd like to announce. If you have questions during the presentation, please post them into the chat. You can also raise your hand and then unmute yourself when called by the host. Feel free to ask questions during the presentation. We'll bring them in the Q&A section in the end. And I will pass it over to Viljo to speak about his topic.
Okay, superb. So we are going to talk today a lot of accordion and tuning theory, also some basic physics of wave motion and so on. And these most of these ingredients what I'm going to give you is going to be also applied to more or less every instrument. So I think we can go directly to the first slide and start with basics, the sound. So the sound is basis of our everyday living. And in physics, the sound can be explained with wave motion. In the picture, you can see 6 different kind of types of wave motion interacting with something. So let's say we have transmission. So if we have medium, similar kind of medium, it can pass forward, or it can reflect, especially if we have hard surface with a high density. So then from air, let's say to rock or to glass, there will be reflection. Refraction would be just basically just bending the wave, and I think the best way of describing this, if you are looking to the water and you can see a fish, but it's not exactly there where you can see it. It's a slightly different place. Diffraction, the picture is a bit small, but there's the red line and small gap And when the wave comes towards the red line, there's a MOS gap, and after the gap, it spreads. Of course, in acoustics in general, absorption is a very big thing, especially if you talk about having a theater or some kind of display room. There's always thought about the acoustics. And scattering, the last one. In accordion itself, the most biggest things what comes to the wave is the reflection and diffraction, what I think. Of course, absorption happens to, let's say, felts in the melody and bass side, but not that much actually. So when we have sound, we have always some kind of movement. It can be a drum, a membrane, or it can be in accordion, we have the reed, what is moving. We can clap our hands. There's always some kind of movement. And when we are clapping hand or have some kind of noise, so we are making movement to the medium. The atoms, the particles in the air, they are starting to have wave motion. And this wave motion goes in the space until it hits something, can reflect or can absorb, and so on, as described earlier. If we are having amplifying system, some kind of PA system, so then we have to have microphone, and we can change the wave in the air to electronical impulses, to compute or whatsoever we want to do, and then back to speakers and back to air. And in the end, we are going to have the hearing and the understanding of the sound. And depending on what kind of sound it is, something happens very close to the ear, like in the start of the ear, and some understanding of the sound happens in the brain. So it's not totally clear always what happens when, but I will explain at least some parts what is important to the tuning. When we have sounds, waves, we can understand a sound with a pitch. So there is some kind of level we can hear it. It can be low, it can be high. Or we can have noises what we cannot determine exact. Is it going to be a high pitch or low pitch? Let's say if you hit a drum, so we can understand it's a low note, but we cannot determine exact. Is it a certain pitch? When we go in the sound to the wave, only a pure tone we can produce is a sine wave, or pure tone, you can say that both way. And in normal living, we are not hearing this one. It's always computer made. Let's say some church bells could go very close by to this sine wave motion and sine wave. But in practical everyday living, it's always more complex than that. Good to know in sound is that it's always working in impulses. So if we have one spot, we start to have a sound, let's say a speaker. So the new sound can never reverse the sound which already exited from the speaker. Although it is possible to muffle the sound in the other end, let's say we have two speakers in certain distances and a person in certain distance, and they have same sounds, but the distance is different. So in theory, they will invert their amplitudes. So the equation for wave is shown there. So the velocity equals to wavelength times frequency. And I have calculated there just for example the wavelengths, what can be what we are listening normally, and these are having some additional aspects as well. If you are in thin atmosphere compared to have next to sea level, it's different a bit, but approximately. So the 440 hertz is having wavelength of 75 centimeter, and if you go to C5 in Helmholtz markings, so almost 4000 hertz, so that then the wavelength is almost 9 centimeters. And in the pictures you can see two types of wave motion. There is the transversal wave and longitudinal wave on the bottom. And here you can see how they work exact. So basically what you can see, the longitudinal waves, they're just pushing the medium forward, and then what pushed comes back on the zero energy level. The transversal wave is perhaps easier to understand. So there is, let's say we have a full stadium, people watching football, and they start to put their hands up. Let's pretend that the one person is an atom, and the neighbor atom catches the energy from the neighbor until it goes up and down. So that happens in the transversal wave. In the tuning, there is some terminology we have to understand. The very basics, what we need to understand is the hertz. And hertz can be calculated only if the tone is having frequency. White noise or similar, we cannot have hertz calculated because the sound wave has to be oscillating sound. And it's determined that one oscillation in a second is 1 hertz. And therefore 440 hertz is oscillating 440 times per second. So quite simple. Not that much needed though, but also good to understand is the energy of sound. And we are using the watt as the energy presentation power. And when we have some kind of energy divided to area, then we have sound intensity. And it's very good pinpoint out that if we have 1 watt of energy in a square meter, we will feel it as pain. It's a lot of energy. And the human heat, we can hear this 2.5 times minus the power minus 12 watts per square meter. So our ears are rather sensitive actually, and this outer ear is very good to catch the sounds. Furthermore, if we go from the intensity to more understandable levels, we are having decibels. And decibels is actually the intensity as a relative unit, a measurement of sound volume. And it works logarithmic scale. And more or less everything we are talking today works in logarithmic scale. Basically, if energy level goes higher, so there comes all the decibel is also interacting. I have written there the decibels when the sound pressure doubles, the intensity trebles, so it comes 4 times bigger. Yeah, let's go to the next slide. Also, one very important thing in accordion tuning or tuning in general is the understanding of scent. And the scent was presented in late 19th century in England. few decades after the equal temperament was established and come to common day usage. How we determine the cent is that it's 1/100th of a half step in equal temperament. So if we go to C to cis, it's 100 and so on. And full octave would be 1200 cents. And I note here that the cent is always an interval. So it has a starting point, it has an ending point. So then we can calculate a cent. And somebody can use this kind of D plus 4 cents. Okay, if you're making any calculations, don't use that. Just use the numbers, let's say 386 cents. The exception, what is okay on my behalf, is the marking of tremolo to tuning. So after tuning, you can mark to accordion what kind of tremolo you have done. If you're doing with the cents, it's rather okay, besides the analog side with the beats per minute or beats per second. And this cent was invented actually to clarify the different ratios. Some of intervals are having ratios which is hard to understand. I put here an example of 2 16/9 and 7/4, and we cannot determine exactly easily which one is bigger and which one is not. But with the cents, we can say quite accurately. And the formula is presented there. And basically, there is 2 parts. So you have a fraction. In this example, I have put perfect fifth, 3 to 2. And then there is the standard digit, which is calculated separately. So you don't need to put that k always with a logarithmic. You can just use the number 3986 and you will have an average result. And here we can calculate that the pure fifth is actually 702 cents, not 700 as in equal temperament. Forward. Many of these understanding the sound happens in our ears and brains. And the range, what we can hear, is approximately from 20 hertz to 20,000 hertz. The picture I have put there is a bit Finnish language, but I walk you through. In the bottom, there's the frequencies in logarithmic scale. It starts with 10 hertz, and then there's 100 hertz, 1,000, and 10,000 hertz are marked there. And I have put straight black lines to pinpoint out the note A's in different octaves. And as we know, everything works in logarithmic scale. The note 440, if we go 1 octave higher, it's 880, so it doubles the frequency. 1 octave higher, it doubles again, and so on. But when we go to very high notes, around 8,000 hertz or so, we can hear that we are having a high note, but it starts to get very hard to understand what is the correct pitch for it. As well, the ear makes it the understanding of the sound different. We need more energy to hear the low voices or notes than the high notes. On the picture there's the red line in the bottom. That is the step when you can hear something or you cannot hear something. And if you are playing a chromatic accordion and just going the scale up and down, there is some points when you can hear some notes stronger than the others. So this is one of the reasons we are able to hear some high frequency more easily than other frequencies. Also, very interesting thing is the resolution of our ears. So if we are taking this 20 to 20,000 hertz range and divide it equally, so we are approximately able to hear 1,400 different levels, notes or frequencies. But it's not that simple for word, because in the low notes we are hearing different amount in an octave than in the high notes. So we are able to, in the high notes, we're able to determine more accurately the pitch. Also, don't go that fast. Also in the ear, understanding the ear function, it tells why we are listening or hearing vibrate or tremolo. And one thing also is very important when we have a sound, a sine tone. Okay, that's a different thing. But if we have any kind of tone which having these overtones, so the human brain is understanding tone with the full spectrum of the tones. So if we take one partial of or one overtone away, we can still hear the same note before the change. Okay, now we can go forward. When we are listening notes, we have so-called just noticeable difference. And this is can be checked, or you can listen to changes if you are listening one tone at a time. If you look to the left side chart, there is the frequencies on the bottom and frequencies on the y-axis as well. If we take the 400 hertz and calculate forward higher, there comes one line and almost two lines, so 2 hertz. That means that if we have 400 hertz and listening that and changing to 401 hertz, we most likely are not able to hear the difference that good. But 402 hertz, we are already able to hear the difference. And if we are making two voices at the same time, 2 notes, next slide, please, then it's different. The ear functions differently, and Harvey Fletcher brought in 1933 so-called theory of critical bandwidth. And this chart we read same way than the previous chart, but we are playing with 2 notes at the same time. And before this theory was presented, we had dissonance. Okay, there were dissonance, but why we had dissonance? So this theory explains why do we have it, or actually where do we have the dissonance. The why happens in the ear, explained later. So the dissonance is something what we don't like, what we are keeping bad sound in general. And if we have an interval, 2 frequencies too close to each other, then we are hearing dissonance, and this explains it. Let's take again on the bottom the 400 hertz as an example and go higher to the line. It's approximately 70 hertz. So we have frequency interval 400 and 470 hertz. Within the range, we are hearing dissonance. Okay, if we have 402 hertz, 410 hertz, then it's not that bad. But when we go higher and higher in the frequencies, the dissonance comes worse. Until we go further, the interval comes bigger and bigger, and then we start to hear 2 notes. And I think what's on the next slide we are able to have some examples. And first, we are going to hear a sample of just a single note, 440 Hertz, and it applies second similar notes. And you can hear that the note amplifies. And these notes are made with a pure tone sine wave. So it's a bit pale sound, but you get the point. So no tremolo there at all. And then there was small tremolo. And now we can listen to example 4, 5, and 6 directly. So there comes always 1 Hertz difference more, so the tremolo increases. And these tremolos happens in the tone fundamental, the lowest frequency. That's the difference what we are hearing as tremolo. And now we can go further and have much bigger Hertz level. So we have much bigger dissonance, and we have, let's put the number examples 7 and 8 in one go. So what did you hear was the dissonance, and when we go further apart, it starts to be clear, more clear sound, almost a good interval. And in the very end, the 9th sample, sounds like a dead end in the phone, but that's an pure interval there. So that's the how the frequencies interacts together and makes the tremolo. Okay, forward. And why do we hear the tremolo? Well, we are going to the ear now. So sorry about the Latin over there. Wikipedia was extremely good with the pictures, but let's try to, I'll try to guide you properly forward. So on the left picture, you can see the ear, and when the sound wave, the pressure changes, comes to the ear tunnel, it starts to vibrate the eardrum. That vibration goes to the bones, which are making the vibration stronger. And the last bone is connected to oval window in the cochlea. The cochlea is the circular shell-looking thingy in the picture. And that's the area where we are having the sound receptors. If we cut the cochlea from the middle, then we can see on the right picture exact what is in there. So the sound goes to the vestibular duct, that would be the higher scala vestibuli, and also the tympanic duct. And between these are the cochlear duct. And when the sound moves there's liquid in this vestibular and tympanic duct, and it will move the middle area. In the organ of Corti, there is 4 rows of hair cells which are connected to the plate in the center of the picture. And when that moves and the hair moves just slightly, we are able to have impulses to our brain. Next slide, please. This cochlea is presented here more carefully, or more simply, actually. On the picture on the left, you can see the arrow and the bone where the sound or the sound wave or wave goes to the cochlea. And in different areas, the cochlea is able to understand different frequencies. The high frequencies are in the very beginning of the cochlea. And further we go end of the spiral, there's the lowest frequencies. And that's a more simplified version, the middle of the picture, the middle picture. So basically, our ear is making that we cannot hear higher or lower frequencies. And also because the hair cells are very close to each other. And the dissonance, if we are having 2 frequencies very close by, it will also move the hair cells very close by. And that we might feel unpleasant. And if Florin can put now the video on, so it's a very short video, or should we have it also only as a link? I don't know. But the video itself at least explains very, very good how the sound propagates the ear.
We'll put it as a reference.
Okay. Okay. So then we can go forward. So now we know that ear works as it works. We go back to the sound in physics a bit more. When we have sound or 2 sounds, there is sound interference. Always when there is sound, it can be a reflected sound, or it can be 2 sources of sound in a space. They will interact always. The frequencies can reinforce or weaken each other depending the frequency phases. So when we have the amplitude in the very first picture I showed you, so if the amplitudes are just the opposite, they will minus each other, so it will be 0. That's good to understand also. Some years ago, my friend who had been working with microphones a lot told me that he calculated once if having a lot of microphones inside the accordion grill melody side. So he calculated that the first microphone took the frequency, like frequency A, like that. But the further apart of the microphone, the amplitude was exact the opposite. So the second microphone make it so that we had suddenly a note which was not clear and bright anymore. It started to come a bit worse, muffled sound. So that's very good to understand that how it works. Then this, I have put here complex and combined sounds. Complex sound means pretty basically everything else in the sound world except the sine wave. So if there is overtones, some kind of color in the sound, then it's complex sound. And when 2 sounds comes together, it will come a combined sound. The tremolo we were just listening earlier, those are combined sounds. If you open the sound of the sound wave, you can see it's a complex, it's not sine wave anymore. One perhaps not that important in accordion compared to violin, for example, is the resonance, what happens in the sound, or wave motion in general. In Finnish language, resonance can be translated to so that like a sound which works alongside. So if there's a vibration or resonance, something what gives sound, and the sound energy start to vibrate something, so that's a resonance. And very good example, this is a violin. The violin body is tuned with the strings to the same frequencies. So one string is having resonance with one area, one section of the violin more than the others. Forward, please. This is basically just saying the same thing what I just said. When we have combination sound, we can have plus and minus calculation. And actually, the next two pictures explains this better than the text itself. So let's pretend that here is the biggest circle line is the fundamental, and then we have higher frequencies as overtones. So we have 1, 2, 3, 4 different kind of partials here. And when we combine these together, we are going to have a combined sound, which can be seen in the next picture, please. And in accordion, we can see a certain pattern. In every instrument, we can see a certain pattern. So this is how it works. You don't need to know how it's calculated. The computer does it for us, luckily. The complex sounds are always, accordion sounds are always periodic. There is oscillation. This example was it Fish, I think? And you can see a certain pattern. The peaks are always on the same area. This sound wave is transferred to spectrum, however. We can see the overtones. That's in the next slide. Oh, almost on the next slide, sorry. So the overtones, when we rip down a tone to its partials, so we have the fundamental tone and overtones, and that has been kept as the basis of the major scale. It's basis of the intervals, how the sound color, tuning temperaments even, and the history of Western music. And all notes whatsoever, they are having overtones. The strongest fundamental partial is the what the tuning meter can deduct or can find easily. But it can also false, because if the higher frequencies, the overtones, if some of them are very high and strong, the tuning meter can jump to that overtone. In the theory, normally approximately 20 overtone is shown or marked in the theory books. There is much more, but that's enough for us. I think we can go to the next slide. Here's the same Fish tone note you just saw, and this is the spectrum of it. And in the spectrum, we can see the partials. So the highest peak on the left side is the fundamental one, the lowest note, and then the peaks higher on the right side are the overtones. We can also see here many other things, as in like if the column or the peak is wide and high, then it's having more energy compared if it's a low and narrow. Also, we can see here that there is no noise on the bottom. So the peaks are very clear the noise, background noise or softness of the sound is very limited. So it's very clear sound. We can see it here very clearly. And if we are turning this spectrum to each notes, we cannot determine them exact on the note lines because they are frequencies, and notes are normally referred to equal temperament. Well, not always, but in this case it is. The overtone series can be calculated always. So the fundamental is the lowest one, then the first partial or the first overtone is 1 octave higher. If we multiply the fundamental by 3, we get the third one by 4, and so on. We can calculate a series of notes. And in the next slide, there is more accurately told that especially the third overtone is a pure fifth from the second overtone, and the fourth to sixth overtone, you can just check the numbers and corresponding note for that. There it comes the major chord, C, E, and G, and that can be kept as a basis of a beautiful major as chord. If we take the next overtone, then we have the dominant seventh chord. And if we go even further to 10th, 12th, and 15th overtone, we have the first minor chord. But I think it's more just how we are understanding a tone, because the higher we go in the overtones, the volume comes much lower. The seventh overtone is 29 times quieter than the fundamental note. So there is a formula how to calculate it. I think we can go forward with this one. Now we are focusing a bit to the tuning, and I have here, I'm referring all the time to the equal temperament, and now I have a chart here of equal temperament and overtone series. And note that this is like a starting point is the fundamental note, and when we go higher into frequencies, they start to variate. Especially if you take the E, the fifth fundamental, or fifth partial, so we have already few hertz difference. That is one of the reasons, the equal temperament, why we are having small tremolo, and it comes because of this difference between the overtone series and what we are normally tuning. Next. The same series can be calculated easily. So pretty basically, a major scale can be calculated so that you take a note and add always the first overtone frequency to the fundamental frequency. So if you do that, you are able to have the scale. This it would be a major scale in this case. Let's go forward. In the overtones, we are listening overtones when we are making tuning. It can be pure tuning when we try to have all the tremolo go away. But in equal temperament, we want to have a bit untuned in tuning, so it would be equally untuned every place. So there would be no bad dissonance in any button or any interval. If we are making an octave, so let's say here the 440, 880 hertz, and because of the overtone series, there's no tremolo between these octaves, so it's always sharp. Normally in accordion tuning, we are using a lot of fifth and fourths, but thirds not that much in chromatic tuning. Can be used. Piano tuners are using it. But here we have marked yellow and green, the overtones, what you are listening when you are tuning. And one way of making this tuning equal temperament is that you have a perfect fifth first. You make it with no tremolo, and then you make the fifth a bit smaller, how to say, drop the higher note a bit. So you have small tremolo there. Same on the fourth tone overtones for interval. Sorry. If we would be taking the third interval, it would be the fifth and fourth overtone what we would be listening. Yes. We have something still there, the tremolo thing, I think, yes. In the very beginning, I said about the tremolo a bit. I put here examples. So we have hertz, and then we have the beats per second in this case. So if you are making a tuning, it would be nice for the next tuner to have a marking, what is the tuning level. So 440 in example, and put 8 cents as a tremolo marking. So it would give 2 beats per second. This is quite good way, but if the frequency changes, the amount of tremolo also changes. People are using also beats per minute or beats per second. It's a bit more labor intensive, as in you have to have a metronome, you have to listen, you have to think about the rhythm, and then you file the rhythm to the reeds, so we can have tremolo. It's that's actually perhaps the most accurate in that sense, that if we are talking about 2 times per second, so we calculate like that. But I keep it best to have tremolo markings with hertzes, and that's because we are in logarithmic scale. The 440 and 1442 hertz in an example is referring here to the first line with 8 plus 8 cents. But we can also see that it's not exact 2 beats per second. It's less. And if we do the same thing 1 octave higher, the beats per second drops a bit compared to the using cents and so on. And then the 1 octave higher, it's even more. I think everybody's having their own markings of how they are marking the tremolo. But I think these are the three types you can compare to each other. I think, did we have any slides? No, I'm happy. I thank you, everybody. And I think Florin takes it from here.
Thank you very much, Viljo. So we will open it for questions. Let's check if you have something on the chat. Yeah, go ahead.
We did have some questions here in the chat, which some have tried to answer, but let's go back to one that was asked a few minutes ago, so that Viljo can explain. Where is it? At what point, this was the question, at what point does the dissonance change to an interval, and how is it different for every pitch? What's the formula for the point where it changes to an interval? This is a question regarding the part on critical bandwidth, when two sounds are close together. When the far apart they go, we start hearing them as 2 notes. So how to calculate that?
I have no formula for that one, but the chart is ish. You can have a look approximately. I think you can Google for a proper formula for it. But basically, the dissonance when it goes over the interval can be said it's an interval. We can hear two separate tones together, and before that it's more towards to the dissonance. I hope I answered good enough on that one.
Okay, so thank you. Let's see if we have other question.
Okay, to ask a question here, this is Mauro.
Hello.
First of all, thank you so much, guys, for the presentation. This is fantastic material and an excellent way to present it. I was thinking about what you were talking about at the beginning regarding intensity of the sound. I work tuning. I work with bandoneons, and when I am tuning the instrument, I normally try to play the notes somewhere between piano and mezzo forte, so kind of in the low range of the intensity of the sound. But after I have done the tuning, I try to take the note to forte state, right, and see if the tuning is holding, right? Based on what I understand from what you said, intensity does not impact frequency, right? Because the question that I had in my head is, by changing intensity, am I changing the frequency of the note or not, right?
Intensity could be explained more like to volume. When you are tuning, it's more to the airflow physics. If you are having this constant pressure, the tuning is made to that pressure. But in bandoneon, you are making quite a lot of accents and strong and very gentle pianissimo playing, and then the frequency is always a bit different while you're playing. That's a reed physics. Is like.
Got it. Okay, so there could be small differences depending on the airflow.
Yes.
Let me just say something that in the case, I think what Mauro is asking shows us that it depends on the instrument we are tuning. What is the thing that the element that's creating the sound? Because the reed does not create sound the same way a wind instrument like a flute or a string. So it has different physical characteristics, and reeds, accordion or bandoneon, whatever the material, whether it's steel or bronze, they have generally an issue with the higher the pressure, the lower the frequency of the reed will be, meaning the stronger we push or pull on the bellows, that reed will play a lower note. And this also takes us to the quality of the reed. So that's why low quality instruments like Chinese accordions, or at least the low end of Chinese accordions, where we have low quality reeds, you have a lot of oscillation between the tuning, the final tuning, because the reed doesn't hold the tuning in high quality reeds, and especially if the reed blocks are well built, and each cavity is built accordingly to the size and dimensions of the reed, then you can minimize this almost to zero. But it generally, I think the point to keep in mind is that this is a problem with the instrument. I guess you can also say that if you blow a wind instrument, there's also a tolerance where when you blow harder, the sound will begin to either distort or get out of tune. So this has to do more with the physics of the actual element vibrating in this case, if that helps understand.
Totally. Yep. Thank you. Thank you so much, guys.
For me, if I tune an accordion, I start today with a Mingashini converter. Look to find a middle way of intensity of air pressure, and look for if it's piano or it's fortissimo. And if I tune it, I look so how is the range or the intensity is the player are playing with this instrument, and so I try to tune and find a middle way of the intensity of air pressure, how I can tune it. And if I find a note or a reed, if maybe Uriel explain this later, or Viljo, I don't know who wants to make this. If you have a big difference to the normal frequency, like A1 440, and you play piano or very silent, and the frequency fell down or go high or pitch high, so it's something wrong with the reeds. So it's my method. Yes, Eva?
Thank you very much.
Got it.
Yeah. So, do you have any more questions?
Yes, Seba raised a hand.
If anybody wants to ask a question, speaking rather than in the chat, this is the moment to do so. In the meantime,
Yes.
Yeah,
I
please.
have a question. Hi,
Go.
hi everyone. Thanks, Viljo, for all the information, and Uriel too. It happens with my accordion. I have a Victoria with 64 notes, and I see in the middle part of the buttons, in the right hand, the tuning is very stable. Like if I play pianissimo or fortissimo, it changes about 1 or 2 cents between. But in the low end, in the right hand, the reeds, for example, the E1, the first one in the bassoon, it can go from 0 in piano to -30 in fortissimo. And that doesn't happen in the left hand, which has the same note, the E1, but the reed is bigger because it's from the bass. It can behave like from 0 to -15, right? 10 something. But I don't know if a reed is bigger, it can hold the tuning better in more pressure, because that's what I see in my accordion. I don't know if this happens with your accordions.
You mean there's a banding of the notes if in deep notes?
Yeah.
Well, I think depending of the instrument and how the reeds are made, big reeds especially can be very good to if you play gently, they are playing nice. When you increase the volume, how the reed is made, it starts to fight against the airflow, and then the frequency drops downwards. So,
yeah, that's what I see.
In general, if we think about tuning, so normally the smallest piccolo reeds, they will in time go higher. On the low notes, there is a bit both ways. Some accordions having the lower notes are going higher, some is going lower. And if you push and pull, the lower reed is normally lower in tune than the higher reed, what you can see.
Yeah, because
Also,
I know they are good reeds, like Salpa handmade reeds from 1994.
Yeah, but some of these are very personal in that sense that every accordion is having different types of reeds, even if they come from the same factory. They might same factory made reeds differently 20 years ago what they're doing now. So they might have different ways of working also. But I think Uriel can talk this about more in the next session, I think.
Okay, thanks.
Yeah. But I think in general you can picture that smaller reeds, higher notes, have their flexion point, the part that vibrates, that moves, is closer to the tip of the tongue. And on the other hand, the bigger reeds, the lower notes, have that movement point closer to the base. Right? You see more reed moving back and forth. So this has to do with the profile of the tongue, right? How it's grinded. Usually there's a round profile, but this really has to do with the, if we can say, the secret of the timbre, of the color of the reed, and what makes reeds very different from one another, without getting into what's good and what's bad. But some reed makers will prefer to produce a reed that is richer in a certain area of the harmonics, which gives it a certain color, a certain timbre, a certain sound. And the downside of that could be that it would be very weak in that flexion point. So the other extreme point of this would be thinking about making the reed as strong as possible so that it won't get out of pitch when you push on the bellows, but maybe that will take you to a drier and a less rich and warm sound. So every reed maker will try to find the best balance between all these factors. So again, just to add to what Viljo was saying on your comment on the reeds that are Salper reeds from the Middle. So I will talk about this whole reed thing in a different webinar, which is a very interesting subject because there's so much to be said and discussed, and there isn't one correct view. But it's very difficult to judge reeds by their maker because of what Viljo said. Technologies and methods change over the years. And the reed is definitely not the only thing which gives an accordion its sound. I mean, the reed blocks make a huge difference. So an extremely well-made reed with a poorly made reed block will not sound as good as an average reed in an extremely well-made reed block. So there's a whole combination of factors, which makes it pretty much very complicated sometimes to get to the core of the problem.
Thank you, Uriel.
Yeah, Cook.
Yeah, I have a question towards the tremolo tuning. I have a Cnc-milling accordion, which I am repairing, but I can see in that accordion that the tremolo voice is not as far apart as I have heard it should be. What do I mean by that? For example, if we take a 2 beat per second calculated into every voice, then you get a fairly straight line, if we put it in a graph, where this accordion has a lower distance on the lower notes than if you put that 2 beats per second, for example, into the lower notes. Why do we tune less distance on the lower notes, for example 10 cents on the lower ones, and then not 5 but maybe 8 cents on the higher ones? Why doesn't that line become a straight line?
I think there is a huge amount of different kind of tremolos. In Finland, most of the tremolo tuning, the lowest notes are having more cents compared to midsection. And then if we go to high notes, the cent amount goes smaller and smaller. But in practice, the tremolo would, let's say, just a basic tuning that from if we go 1 octave higher, the tremolo can double, although the scent difference goes smaller at the same time. But in this your case, did I understand correctly that on the low note tremolo there is less tremolo than in the middle?
Yeah, but if you look at the beats per second in the lower notes, you will have less beating than on the higher notes. That's what I can see from what I have.
Yeah, this is actually the normal kind of tremolo that you have a slower one in the deepest notes and a quicker swing. I have to say swing in the higher notes. That's correct. And you ask if I understand it right, why we tune the lowest notes with a bigger difference to the higher notes. So like A, we have like 25 cents and A4 like plus 10 cents. That is your question.
Yeah, kind of it is, but if you would have the same beat per second on the lower notes, then the cent difference should be more than the double than what it is at the moment on the lower notes.
Yeah.
So actually, if you have the straight tuned and a straight line, and then the other one you make a curve out of it, then on the lower end it's around the half. Let's say 1 beat on the lower notes and 2 beats on the higher notes.
Remember, we are working in a logarithmic scale. If you make, let's say, 2 cent difference, and then 2 cent difference in 1 octave higher, then the beats per second doubles.
I totally understand. Just give me one chance. I totally understand that the scent cannot be the same thing, but the way that the accordion has been tuned is that it has less beats or swing in the lower notes than on the higher notes, and that's what I'm kind of pointing towards. Why is that done like that?
Go ahead.
So if you think about in general, if you have a band playing and there's a bass player, the bass player is never playing 2 notes close to each other because it sounds horrible. It's a dissonance. It's within the critical bandwidth. If we are having big reeds, low tones, and we are having a big tremolo, we will feel it unpleasant. And it might be also partial the different cultural areas. Some area wants to have different kind of tuning than the other ones.
Yeah, I can understand that. Yeah.
I think I can answer that better because, for example, in my country, it happens that the old tuners, like in 50 years ago, they knew that, for example, the A4 that was tuned to 440 and the other one 443 or 444. But they didn't know that the next octave needs to have less difference. So they tuned all the notes in 443 or 444, and that happened that the next octave had more tremolo, and nobody knows, like, nor the players, neither the tuners. And that kind of makes that a kind of cultural sound that everybody accepts that the next octave sounds with more tremolo in my country, for example. And I am doing the right way, that the other octave has less distance, so the tremolo is similar from one octave to the other, and everybody perceives it as it's wrong. And it's just a cultural thing. Like, my country got used to the bad sound of the next octave. I don't know why.
I mean,
Maybe
I
that's
think that
what happened.
there's a lot that can be said about it's definitely a culture thing, and that's why there is no right or wrong tremolo, because if in one region or country accordions have been tuned the same way for the past 50 years and everyone likes it like that, then that's just what it is. But I guess we can say that in Europe, where accordion was developed and produced historically more than any other place in the world, had a bigger impact, a bit bigger influence, and that's why most tuners go by those the ideas of European builders and technicians. And this the general, very general rule, if we can speak about rules in tremolo, is that in order to, it's like Seba was saying right now, if we take hertz as our parameter to define the difference between the two musette reeds, so we'd have A4 and 440 hertz, and then the other A4 will be 442 or 444, whatever you choose. So that's the middle of the keyboard, right? Towards the lower notes, you would have to increase the tremolo, and towards the higher notes, you would have to decrease the tremolo, just because of a thing that has to do with critical bandwidth and what we were speaking about before, that what is pleasant to our ears, which is also very subjective, but generally we tolerate less tremolo towards the high notes, as Viljo was saying before. That's why we would lower the difference between the two musette reeds towards the higher notes. And the lower notes, since we have a bigger bandwidth tolerance, which means we also need more difference between those two musette reeds in order to hear that same tremolo effect, so there we would have to increase the difference. So like I was saying, the general rule is that it's a curve, it's not a straight line. You can't tune all reeds on 440 and 442 or whatever the difference you choose. It's always going to sound okay in some areas and not so okay in other areas, depending on what you do and depending on where you want to go. So there's going to be a curve, and it's maybe a little bit hard to understand that there's three concepts here, like Viljo was saying. There's hertz, there's cents, and there's beats. So the beats is the only thing we actually hear. It's something we perceive in our ears. We don't perceive cents. Cents is just a number that helps us understand intellectually, like theoretically, something, but we don't hear a cent. We hear that wah-wah effect of the tremolo of the beating. So the beat, if we take, just to say it in 1 minute, the curve of the tremolo over the keyboard, the curve of the beats per second is going to go up, meaning from the low to the high notes, there's going to be faster beating as higher we go. On the other hand, the cents is going to go down. There's going to be more difference in cents in the low notes and less difference in cents, and the high note to compensate for this. And this has to do with all these factors: the critical bandwidth, how we perceive, and all the algorithmic skills algorithmic calculations that complicate the situation a little bit. So this is, like I said, generally the rule, but like Viljo was saying, maybe in Finland they like the low notes to sound drier, and that's just how it is. So I don't know if this helps to understand a little bit. It's definitely something that needs a lot of talking about.
Yeah, no, I asked one person, and he explained me that you tune the tremolo to 2/3 actually, instead of like going upwards in octaves, moving and calculating 1 to 1, you calculated 2/3, where actually my accordion is a little bit flatter than that. And that's why I am saying that on the lower notes, I might have 1 beat per second, but on the higher notes, I will get 2 or 3 beats per second. And musically wise, it sounds wrong to me, but it doesn't sound bad to my ear. So it has, yeah, it's what it has been done in long term, in many years.
Yeah. It makes sense what you're saying. I mean, I imagine back over 100 years ago, accordion builders playing around with all these things and just tuning one reed, one set of reeds to 440 and the other one all 443, and then trying to improve that. So sometimes the math isn't the same as the ear. So the way they found to improve is just to make that curve where the tremolo will sound to our perception as human beings more how do you say, more adequate, more coherent over the whole range.
Exactly. Well, thank you.
So thank you very much, guys. So let's see if we have more questions. I don't see any hand raised, so we should wrap up. Thank you all for the questions, for the dynamics, and if you want to find us, we are on Facebook, Instagram, and also we have a YouTube channel. We'll post the video afterwards, and don't miss the next session, the next webinar on accordion tuning on the 25th of November with Uriel. So thank you for your presence and enjoy the day. Bye bye.